So in this case, this is now QLearning, but continuous actions. All of our robots are okay. In theory, nice, smooth, continuous control. Although in actual reality, there's no such thing as a continuous number on a computer, but this is not a signals analysis class. This is a robotics class, at least a robot learning. So here now it's like, well, how do we translate a lot of the ideas from QLearning and deep QLearning and actually be able to optimize for continuous action spaces? So DQN is still based on this form of Q iteration, and it has to perform this. And this is really where the heart of the problem is going to be in order to be able to do this for continuous action spaces. So if this thing is continuous, it's no longer possible to just make like a Q network that has some number of outputs and just do like, argmax on it and give an output that include that in the gradient. Now somehow this max needs to be done over a continuous action space. It's true though, in like the last paper, like for the Qt opt paper, they did this like basically explicitly at every state. So there wasn't as much of a process doing this encoding exactly what should always be the best action. So it's possible, and there's certainly a couple of papers on like using chem. This was basically Qt opt here. That was just doing some black box optimization. But we really don't want to have algorithms that have to do this at every step, especially if we want algorithms that have to like make decisions in real time really fast. Like if we're going to use RL for self-driving cars, who knows, maybe we will or won't be the final answer for that. But it does mean that it's going to have to make decisions at a pretty high frequency. And that if it's making an optimization every time it goes to make a decision, the next time it visits that state, it might actually get a slightly different answer. So it's not always going to be optimal. It's going to depend on how much compute is in your car. So at least I certainly don't want an answer that depends on like how much money I spent on my car because it has a slightly better computer or something like that, and it'll give me a slightly better answer. We don't want any kind of ridiculous like that coming into the universe. We've already got enough ridiculous stuff to deal with these days. Um, so, so then basically, can we be able to optimize some model with gradients that'll be able to capture this process? And at least one version of this is to use maybe some simple function class. You could kind of think maybe one option for that Qt opt paper would be like instead of just using straight chem and doing that optimization, after every optimization is done, at least like do supervised learning on some policy that remembers that optimization that was finished, and then start from there next time is like I'll call that like the really basic option of what could be done, but we could still do a little bit better. So what happens really often is basically this process. It's like, can some model now be trained that is this max overall actions? Like it gives the best action at this state according to the current Q function. So we're kind of like amortizing the cost of being able to compute this best action and have a model for that automatically. So this means we'll need another model for the policy. So a Q function, the way QLearning worked from before, is it was easy to learn the Q function and then compute the best action from it. So there's like one network. That was the whole process. Now this is going to be different where there's going to be a second network that essentially is now trying to, implicitly amortize and encode this process for what is the best action according to the current version of the Q function. So there's still going to be maybe a bit of this process where there's a Q function that's being learned, and now a policy here that's going to be trying to match the best action in that Q function as that Q function is training during learning. So there's a bit of a challenge in training this process, but I'll talk a little bit more about that on the next slide. But really then, the way that the Q value, at least for the best action, can be computed here is, all right, if this is learned, then the idea is, well, now this model gives the best action, and to get the best Q value, you can just use that model to produce an action, give it to the Q function, it gives the current Q value for what would be the max overall actions. This basically models this function here. Our max overall actions is just the Q function given this other learned model that's being trained to be the max overall actions. Okay, does that make sense? It's kind of like, now we'll embed another model here. And this is at least nice because it starts to give us the hint about what we can do. It's like maybe to train that model, we can just start computing gradients from this Q function and how to change that mu on the right to be the thing that maximizes Q values for the actions that it produces. And that's basically exactly what we're going to do here. So now we just need to figure out how to train this. There's no model, but now because of this, there is technically now a new policy gradient. So this is what's called a deterministic policy gradient. So it's not a stochastic policy gradient because our policy that we're modeling here is just a point estimate. It's not actually doing any sort of like stochastic expectation. It is a version of a policy gradient that we can end up computing given this learned Q function that's already available. So you can look into more of the details, and this is basically what we're going to cover here, but this is the deterministic policy gradient algorithm. It's one of the first, at least like deep deterministic policy gradient algorithms. So like uses a deep network and is still able to train a policy that works pretty well. So here, this is just, we want to be able to compute the gradient for how to change the policy. We just use the Q function. We say that the action actually comes from this policy that we're now modeling and going to be used as the max overall actions. And then from here, this is now just the gradient of how to change this particular model such that it'll end up increasing the actual Q function. So now it's just, we're chaining two models together. One outputs like a single value. We want to make that single value higher and then just compute the gradient for this other policy such that it makes the output of that other function higher. So it's just sort of like chaining two functions together. And then this just gives us our deterministic update. So yeah, you know, like the partial derivative here of the Q function along with the partial derivative here for the actual policy. And then we just compute gradient updates that way. And that's how we update the policy. And then as our Q function gets more and more accurate, so too should, you know, our policy here being able to maximize actual Q values or like sums of rewards in the environment. A bit of the challenge now is maybe you're starting to worry about this, but now there's going to be a lot of networks that are being trained all together. I'll say a lot here. There's certainly some algorithms that have more, but there's going to be a model for the actual policy. There's going to be a different model and set of parameters here for the Q network. But yeah, don't worry. There's also target networks for both of these. So now there's four basically versions of the network parameters for all of these. So this is taking the idea of like needing target networks to help make this optimization a little bit more stable and still maintain its ability to be able to be a contraction, so that there's going to be a target network for the policy and a target network for the Q function. And there'll be a slightly different change about how these are going to be used, or at least how the target networks are going to be updated. But it's the same concept. And then here we get this slightly longer, now more complex algorithm. But there's only really a few things that have changed. This really hasn't changed much, this sample batch of data. Here, mu of A given S theta is what's going to be technically used as the policy in the environment to be able to sample data. There's a bit of a detail around that I'll get to in a few slides, but let's mostly just go over this a bit carefully and then we'll be done for the weekend. So here now, to be able to compute target values, the target policy, so the one that's a little bit behind, is going to be the one to output an action, and that outputted action is going to be fed into the target Q function, and that Q value is going to be used. So the target values now kind of depend on the output of these two functions that are older versions of what are actually considered the online models. And then from here, just do a very similar update to what we did for QLearning, and now update the policy. in order to be able to like take the same gradient. And now the target network update here is a bit different. It's not, after 10,000 steps, directly copy all the parameters from the online networks to the target networks. It does a different version of using Polyac averaging here, which takes some small percentage, some small portion of the parameters from the online networks and assigns them over to the target network. So often, row here, there's going to be something like, this is stuff from those models. So let's make sure I get this right. 0.99, something like that. So that like, yeah, a very small portion of this is going to end up coming from the new network. So that this will end up being something like 0.01. And then this computed back here will still be like 0.99. So it'll take, 1% of the parameter value from the online network and contribute that over to the actual target network. And it'll do this after like every gradient update. So this is another version of like just being able to have a model that's slightly trailing from behind, but kind of approximates the current output. Okay. Questions? No, this makes sense. Okay. Because really I don't like a single line of this algorithm and the way that it actually ends up working, because they're all not actually reasonable in some ways, but no questions for now. Okay. Maybe I'll at least leave you with this one question that we'll pick up more on Wednesday. Isn't line 8 kind of weird? So like now, at least when we were doing target network updates for QLearning, what was copied was a target network that actually was trained to match the Bellman updates properly. And it was just copying over those parameters. But now this target network is just, let's take a little bit of the parameters from this other model, kind of blend them into our current parameters, kind of like it's making some sort of soup and we just tossed in an extra ingredient or something like that. And this is now the model parameters for the target network may have never actually been any reasonable value for a Q function. Nothing that's ever actually been trained to match the Q value data, ever. But somehow this works. I'll say like somehow this helps, but it still is a really weird concept, at least so far, for thinking about this. But so we'll talk a little bit more on Wednesday about like, well, at least why this works mathematically, but we'll also discuss a little bit more about why this is kind of disappointing and maybe there's some other things we can do. All right. All right, everybody. That's it for today. Have a good weekend. I hear there's more weather coming on Sunday, so go skiing, do something outside to at least kind of conquer the snow and have a good time. Otherwise, do a good job on your homework assignment too. Burn some GPUs around town and help keep it nice and warm around here. All right. Take care.